Okay, so um, what we have now is that we have the energy density per unit wavelength inside the cavity. The energy density in the cavity per unit wavelength is equal to 8 pi kT divided by lambda over 4. And we just discussed how this leads to the ultraviolet catastrophe. This leads to um, a prediction which is much different than what is observed experimentally. It's not compatible with Wien's law. It's not compatible with the Stefan-Boltzmann law. If you integrate this over wavelength, you'll get the total power for a particular temperature, and that clearly diverges because this diverges at small values of wavelength, and that's again not compatible with the Stefan-Boltzmann law. But just to finish this off, what we should do is relate the energy density in the cavity as a per unit wavelength with the amount of power that's radiated into remember, what we're talking about here is a cavity with a little hole, and there's radiation inside. Okay, there's an energy density inside, and we want to know how much of that energy which is inside gets radiated out. And it's I'm going to leave this as a homework problem for you all to determine the relationship between the energy density U and the power radiated per unit area. And what you'll show in your homework problem, okay, is that the energy density again is related to the power radiated per unit area in this way. It's 4 over c. C is the speed of light times dPdA. Okay, so remember, dPdA, as we discussed early on in the lecture, is the power radiated as a function of area through the hole in the aperture in the cavity. So when you plug this into here, you just substitute 4 over c dPdA for U. Then what you find is that dPdA is equal to 2 pi c times kT divided by lambda to the fourth. So we see that we still have this problem. We still have this lambda over 4, lambda to the fourth power, which leads to the ultraviolet catastrophe. So the radiated power mimics the problem in the energy density, and we have this ultraviolet catastrophe. Okay, so I'm going to stop the lecture here because we haven't gotten to the resolution of this catastrophe, okay, which was provided by Planck, okay, but we've already gone pretty long in this lecture, and so I think I'm going to break this up and talk about how Planck resolved the situation in the next lecture, and I'll also probably talk about the photoelectric effect in the next lecture, which then will tie off our section on the early demonstrations and theories related to the quantization of light.